Okay. Okay, welcome to lecture. We're recording now. How is everybody doing today? Good? Pretty good back there? Yeah, so we're going to learn a pretty cool algorithm today and an even cooler one next week that you guys probably do want to make sure you know. Let me erase this from over here. A couple of announcements. There is a HBCU virtual career fair. I'm mostly passing these along from the ACM organization here on campus. Grace Hopper's coming up. If you guys haven't had a chance to go, there are scholarships that pay for you to go. I think NCAT might have some. I'm not entirely sure. I went when I was, I think, a junior in college. Pretty fun, pretty interesting. So if you get a chance, you should go. I mean, there's a ton of recruiting. You get to see a bunch of people. And then there's a Black Wings hackathon that's apparently happening. All of these are like in early February. So that's why I'm putting them here. Homework 2 was released. It's out. It's due next Tuesday. Just a reminder for you guys. I did take feedback from homework 1. Hopefully this is, so the last coding problem in homework 1 was probably like the most challenging coding component that we're going to have to do. So yeah, also just general reminder, if you, I guess another reminder, homework 1 solutions, we are going to release them essentially after the final day that you can submit homework, because we let people submit late for 5 days. So if you guys remember that. So after that is done and you can no longer submit the homework, I will release the solutions. Also, I don't want everyone to do this, because if everybody does it, it's like pretty difficult, but you can submit corrections to try to get points back. But you would email those to me directly. So just like email me to try to like organize that if you like felt like you did really poorly on a particular homework assignment and you want to get points back. If you have the time and you're willing to like submit corrections, email me directly. We'll figure it out. This is a little pie chart into how long people took. So the majority of the class said around 4 to 6 hours for the homework assignment. So that's good. I think that's sort of what I'm targeting. I want this to get bigger. And this 20% worries me. There's a lot of people that are taking more than 10 hours. You're probably trying to catch up with the rest of the class. So at the beginning of the class, you're probably going to spend a lot more time. And then towards the end of the class, once you've caught up, it'll take a little bit less. But this is from the survey that you guys submitted. So if you guys didn't submit the survey, please submit it, because then I can capture your information. I can get a sense of like, am I making the homeworks too long or too short, etc. Cool. Yeah, so lastly, another piece of advice. There were a couple of folks that talked about feeling overwhelmed in the class, that they're not necessarily getting everything that we're covering. And my piece of advice is, it's okay if that's the case. This class is hard. But I think also the main thing like I want you to take away from this class is, one, you're trying to learn algorithms and I'm trying to help you practice, right? But I will say, like, my first internship, my first job, like for the first few years of my career, I did not know what I was doing. And I even now, I still don't know what I'm doing. So like most of your life, if you're doing something that's difficult and something that's worth doing, you'll feel like you don't know what's going on and you're just trying to figure it out. So this class might feel like that at times. Like, I am not expecting you to walk out of lecture and be like, I know everything already, right? Because then that means the class is too easy, or you like already knew the material from before. Okay. So if you're feeling like you're struggling, come talk to me. We can chat. But it's also pretty normal, I would say. And even when you get like your first job, like if you go to, like, I don't know if I told you guys this, but like my first like actual job was like a C++. I didn't know C++. So the whole first like couple of months, it's just like, I literally don't know how to code and I don't know what I'm doing. But you figure it out and you make progress. And hopefully you will see that through the rest of this like class. We will be making progress and you will get better at some things, but not necessarily 100% of things. Okay, cool. Any questions on that? All right, so let's get started. All right, so last week we introduced the k-select problem. So just a reminder from last lecture, the k-select problem is you're given an array of numbers and you're trying to select the kth smallest number, right? So the array is not sorted already. It is in any arbitrary order. We're going to assume that all the numbers are different. How this makes our code easier, but if the numbers were not all different, does anybody know how, like, what's an easy fix to make sure all the numbers are different? Yeah, back there. Sorry, could you speak up a little? Yeah, so one solution is, like you said, you can, before you do anything, if you know your algorithm is going to take linear time, you can just quickly check for duplicates. That is something that also takes linear time, and you can remove them or ignore them. Another solution that a lot of people will do is they will replace all their numbers with tuples in C++, where you include the index of the number as part of the number. Okay. And then you can imagine when you're sorting, when you're doing comparisons, you only ever look at the number itself, but then that makes every element in your array like unique. So that's why for this lecture, we're going to assume they're unique, because it is possible to like forcibly make them unique, either by dropping the duplicates or by keeping the index with the number itself. But yeah. So again, select AK. This is the algorithm we're going to try to solve today. Is return the kth smallest element of A. Here's a couple of examples. I think we covered them at the end of last lecture, so I'm not going to go too quickly through them. I am being a little sloppy with the floors and the ceilings. Just don't worry. Like here, like n divided by 2, like it's unclear what exactly that means when like n is odd, right? So I'm being a little sloppy. There should be like a floor or a ceiling there. Don't worry too much about it. Doesn't affect the algorithm. So I did then ask you guys, how would you solve it? Because you guys can probably already come up with an algorithm to solve this problem, right? Somebody want to repeat what you guys mentioned last lecture? So I give you an array and I give you a value k, and I want you to return the kth smallest. So if k is 1, I want you to return the minimum. If k is 11, I want you to return the 11th smallest number. Yeah. Yeah, so the way I define the problem is defined as like the first smallest is the min. So k would be 1 in that case, but you actually want to return the very first thing in your element after you sort it, right? So that's the only tricky part. But yeah, this is a perfectly valid algorithm in the running time. Yeah. Yep, n log n. So you're doing two things. This takes n log n time, and this is constant time. So the total running time is n log n. So that's the benchmark. That's what we're trying to beat. Okay. And that's what we're going to do in today's class. So again, we do k minus 1 because the way I defined the problem, the k is 1 index, but in code it'd be 0 index. So we can actually, so I did prepare code before lecture where I coded this up. So the link is available on the slides. And let's code it up. So let's code up this algorithm you guys just gave me. I will tell you in utils.h, I already have an implementation of merge sort. This is actually the implementation you guys did in class. So now we're just going to code this algorithm. Somebody want to tell me, how do I start? Well, let's first start by defining the function, right? So what are we going to return? What does the algorithm return? I heard integer. Yes, the algorithm returns an integer. So it's going to return one of the elements from our vector. All right. What do we want to call the algorithm? Okay, we'll call it k-select. What goes in the parentheses? So what are our inputs? A vector, okay, and an integer, right? So let's define, we say a vector of integers. We're going to call this values. And we have an integer called k, okay? All right, so now we write our algorithm. So what do we do? What's the first thing? The first thing you do is you sort the vector. So one thing you will, so we'll do this. So sort it. And how do I sort it? you call merge sort. So this is actually the implementation that we wrote. So we just call merge sort on values. That's going to sort our vector. And then we return sorted k minus 1, right? So again, pseudocode to code, right? So if you can get the pseudocode, you want to try to get the code. We can test it out. So let's do this. Let's try to print this. So what is this? Min element. So how do I get the minimum of this vector A using my k-select? What do I do? So I call k-select, and I give it as input A. What's my input for k? 1. Okay, so let's try that. See if it prints out something. So it's making. It's running. And it printed out. So you can see it here. Min element is 2. Let me add standard NL here. Okay, so that's the min element. Does everybody agree that is the minimum element of this vector? Yes. Okay, so do you guys want to try something else? What other value of k do you want to try? Let's test it out. Yeah. Oh, there are 2 3s. So for this implementation of the algorithm, this is actually always going to be right. But for the one we're going to talk about next, we are going to assume they're all distinct. So it would, you need to tweak it a little bit. But yeah, great question. So let's try the third smallest. Or yeah, Sean. Yeah, this one was the first smallest, right? Yeah, it printed 2 right here. Yeah. Let's try the third smallest, and I will run it again. And maybe try to make this a little bigger. And then let's just, I think this is the last piece we're gonna, yeah, so the minimum element said it was 2, and it said the third smallest is 3, which is also this 3, because there's 2 3s. So the algorithm works. So that should be obvious to you guys. You're just sorting it, and then looking into it, right? So our goal is to be an O of n time algorithm. So how might we think about this? Well, we can think through some examples, right? So like we mentioned, when we use k equal to 1, that's equal to the min. I asked you guys, how might you implement this in pseudocode? So just finding the minimum of a vector. Hopefully, because you guys actually did this for your homework a little bit. I think either it was the max or the min. So this should be familiar to everyone, right? So what is the running time of this algorithm? O of n? Yep, this algorithm is O of n, all right? So, but the difference between this algorithm is we're fixing k. So we're saying k equal to 1. So finding the min is always linear time. Or we can write an algorithm that's linear time. So maybe what you're saying is like, well, what if I expand this idea? So how would I write the code to find the second largest value, or the second smallest value? Sorry. Yeah, so I would pass in k equal to 2, but then can I write a linear time algorithm to give me that answer? So this is O of n, we talked about that. Do you guys see how this? So let's say I want to write this code, which is I want to find the second largest. So again, this is not related to k. This is just I want to find the second largest, the second smallest instead of the smallest. Yeah. Remove an element from the front of the array. Is that what you said? So we don't, it's not sorted. So this time we're trying to avoid the sorting, because the sorting gives us n log n, right? So we know that if we have to sort it, then like we're already n log n, right? Yeah. And you're making sure that the second min doesn't match the actual, but it's still smaller than all the other numbers. Yeah. So does that make sense? So basically you keep track of 2 variables, right? So you start with your minimum and you say, well, my minimum is infinity. Why do I set it at positive infinity, or like a big number? Right, because the very first number I see will be smaller than this one. So it'll automatically pick it up, right? And then I set my second minimum. So I say like, well, this is the second largest. That's also going to start at infinity, right? That's probably fine. I iterate over my for loop. my array. And then basically, there's a couple of changes I make. So I add this check to say, if, so somebody explain, what are these conditions checking? So this is saying if my element is smaller than my second smallest element that I have so far, and it's smaller than my smallest element, then this element is now the smallest, right? So that's why we say, okay, my minimum is equal to the element, right? And my previous minimum is now my second smallest number, right? Because now I found 3 numbers, all of which are pretty small. And now I know, so that's why I said second min is equal to my previous minimum, right? So that's one case where I need to update. And then again, the second statement, what is this checking? This is saying I found a new number, AI, that is smaller than my second smallest so far, but it's bigger or equal to my minimum. So in that case, I only need to update the second smallest, right? So this one, I found a new minimum. This one, I found a new second smallest, right? So what's the running time of this algorithm? O of n, because you have a for loop. So this stuff is O of 1, and then you have a for loop iterating over each element. Yeah. Other way around, the second statement above the first statement. So the order of the statements doesn't matter because they're exclusive. So they're either, both can never be true at the same time. So I would say the order doesn't matter. And I don't know, does anybody else have questions? So like, for sure, I mean, the first statement is checking, like I found an element that is strictly smaller than everything I've seen before that I'm still tracking, right? So my second smallest is now what was previously my smallest, right? And my new smallest is this new element I found. So I do think this code is right, but maybe you can walk through a few examples and convince yourself that the pseudocode is right. And then at the end, you return second min. So still O of n, like you guys mentioned, right? I will say this algorithm is actually not that important because this doesn't work. So you can imagine extending this. So we can try to code it. I actually coded an implementation of this in lecture. But you can imagine, let's say, like, let us keep going. So now instead of the second smallest, I want to find the median of an array using this approach that we have developed. How would I do that? What does that look like? Using the same approach, yeah. Yeah, so I heard you keep defining mins, first min, second min, right? So you say, okay, my min is infinity, then I'm going to have a second min, then I'm going to have a third min, I'm going to have a fourth min. And basically, this is not a good idea because what's going to happen is you will have to define as many minimums and keep. So each time you define a new minimum, that adds another check to your for loop, right? So you can imagine if I'm trying to find the median, I have to define about n over 2 variables. And then in my for loop, I have to do n over 2 if statement checks to like say, like, are you the smallest? Are you the second smallest? Are you the third smallest? Are you the fourth smallest? Are you the fifth smallest, right? So basically that algorithm essentially becomes O n squared. Yeah. Yeah, so one suggestion is there might be a way to make the algorithm work by adding a variable that is keeping track of how many minimums you've seen so far, like first, second, third, fourth. Intuitively, you're on the right track, but what you want to think about is how do you update that counter after you've seen, like, essentially you need to know the entire history of the minimums you've seen. Because if you've seen like 5 minimums, when you see a new number, you might not know where, like whether you should increment by 1 or not for that variable. So if you actually try to implement it, it's a good idea if you try to implement it, you will essentially run into issues into like how to update that one number that you're keeping track of. Okay. Yeah, like we said, this essentially becomes insertion store. So this is again not a good algorithm. Okay. So we've tried, so this is how the process works. Okay, so I gave you a problem. You guys are trying out stuff. You already have an algorithm that works, which is the one you've seen sort, right? We already coded that. So you do have a solution that is correct. And I'm challenging you guys to see, can you come up with an even better one? For minimum, you could. For second minimum, you did. For maximum, you can. For median, it kind of doesn't work out that well, okay? In general, you can come up with a linear time solution for any one element. So there is a version where, like, if I tell you the value of k ahead of time, you can write an algorithm that will return that kth element, all right? But that's not what we want. We want where we don't know the value of k up front. Okay? Does that make sense to everyone? So here's our big idea. So if you don't know how to solve something, you try the ideas that we've covered in class before. So the only thing we've covered in class so far is sorting, which you guys already tried, and that does work. The other big idea is we're going to try divide and conquer. Okay, so the idea here is that we can pick an element from our array, right? So it's not sorted. Pick some element. Don't worry about how we're going to do it. Let's say in this case we pick 6. Okay. And we can actually divide the array into 2 parts. Numbers that are bigger than 6 and numbers that are less than 6. Okay. So again, this might not make a ton of sense to you right now, but essentially you can imagine first, somehow pick some number to split the array. And then I'm going to split the array into smaller and bigger sides. This is essentially like a modification on binary search. If you guys kind of remember that, but we're not sorting the array at all. Okay. We're just splitting it into left and right, right? So basically, I ask, is 9 bigger than 6? Yes, so I put it on the right side. Is 8 bigger than 6? Yes, so I put it on the right side. But I am not sorting. I am just splitting. I'm partitioning my array into 2 parts. All right, so this is the first idea. We divide the array. How long does this take? Yeah. O of n. So we look at each element once, and then we decide where it goes. So it's going to take O of n time. Okay. We do not sort the halves, right? So we're not sorting. If we had to sort them, then it would be like n log n. But we're not sorting. We're just splitting it into half. So now that we have this, say that I want to find the kth smallest element, and I've split the array in this form. Okay. How would you guys do it? Yeah. Right. So we're trying to divide and conquer. We're trying to figure out to which sides we're going to go. So this is kind of reminds you a little bit of a recursive algorithm. That is a good approach. So basically what he said is we'll start with all the cases. So there's one case where, let's say k is 5 in this example. So that means it's exactly equal to the length of my left side plus 1. Right? So that tells me that my 5th smallest element is exactly the pivot I picked, right? Like I got lucky. I picked 6, and if you're asking me for the 5th largest element in this array, it happens to be 6. And how do I know that? Because my k is equal to the length of this plus 1, right? So that's one case. So we just immediately return we're done. And then as you were saying, there's another case where the kth smallest is less than the length of my left array, right? So I know all of these values are smaller than my pivot. So if I'm looking, and my pivot is the 5th smallest, right? So if I'm looking for the 1st smallest or the 2nd smallest, I don't ever need to look at this side. I already know all these numbers are bigger, right? So I recurse on a smaller version of my array, right? Does that make sense? Okay. Now, if k is bigger than 5, can somebody work out what that might look like? Yeah. Yeah. So that is the right approach. You want to recurse on this side, and then you have to do just one thing, which is you need to tweak this index, right? So you actually recurse on the right side, and then you say k minus 5. Because if I'm looking for this is the 5th smallest. If I'm looking for the 6th smallest, which is going to be 8, when I recurse on this side of the array, it now becomes the 1st smallest, right? So I shift over because I've thrown away all of these, right? But the benefit of this algorithm, this suggests a recursive algorithm. So I didn't tell you how to pick 6. I haven't told you how to do that yet. But you can imagine if you had a way to pick some number, this gives you a way to split your array into parts. And then you can recurse into one of those parts, right? Into one of those. So let's write the pseudocode, right? So select AK. So this is exactly what we had before. First, we have our base case for some value of K. Let's say our array is small enough where we want to just go ahead and do the work directly. We'll just sort it, right? So what is the running time of this? It is not n log n. It is not O of n. It's actually constant. Why? Because A is always at most 50. So if you have an upper bound on your input, your algorithm is always constant in terms of big O notation, because this part will never take more than 50 times log 50 steps, right? Because we can plug in the 50. Okay, so that part is constant, and then I just return. Then what I do is I get my pivot. So I say, like, I'm going to write some function that gives me the 6, right? Or whatever number I want. I want to pick a pivot. This is actually the part that is the hardest part, is picking the pivot. Okay. Then I'm going to say, take my array and my pivot, and I want you to split it into left, into right, and into my value, my pivot value. Okay. So I'm just splitting, I'm partitioning it. And then we wrote exactly what we covered. If the length of the left side is equal to k minus 1, return the value, because that means we got lucky. Our pivot happened to be exactly the kth smallest element. Okay. If the length of the left side is bigger than k minus 1, then recurse on the left side, because my kth smallest element is going to be on the left. Otherwise, recurse on the right side, slightly modify, shift over this thing. So this is exactly what we just did, except now I'm including the length L instead of the 5, right? So from our example, we went to the pseudocode. So again, base case is O of 1. Case 1, we got lucky. Case 2, we recurse. Case 3, we recurse. Okay. So this is a valid algorithm, actually. So if you had somebody else tell you the pivot, this works. Does that make sense? Does it make sense to you that this algorithm would be correct, at least? Okay. So I did code it up. You can look it up if we code it, but we're running a little short on time, so I'm going to skip that. There is also a formal proof in the lecture notes. If you're interested in how you would prove this, you use proof by induction. Anytime you see recursion, the formal proof is to use proof by induction. Okay, but intuitively, it should make sense why it's correct. Okay. So now our question is, how fast is it? So the very first thing I'm going to tell you is I haven't told you how to get the pivot, but let's assume that getting the pivot is at most linear time. Okay, so however we get the pivot, it's going to take linear time. Then we can actually write this recurrence relation, right? So the running time of my algorithm has there's three cases. Either it'll be the running time it takes to run my algorithm on the left side, plus the time it took to get the pivot, right? Or the running time it took on the right side, plus the time it took to get the pivot. Or I get lucky and it was just the time it took to get the pivot, all right? So this is the recurrence relation for the pseudocode that we just wrote, where we don't really know the length of L and the length of R, right? So what are the lengths of L and length of R? How big is the left and the right side? Maybe. Should be at least one smaller than the full array, because we always take the pivot out, right? So it should be at least one smaller. But really, the question is, it really depends on how you pick the pivot. Like, it depends on which number you happen to pick, okay? So what is a good pivot and what would be a bad pivot? This is a question for you guys. Maybe let's spend a minute thinking about this. So what would be a good pivot and what would be a bad pivot intuitively for you guys? Well, actually, I'll let you guys think about it for a bit. Come on, chat with each other. Like, what is the worst possible pivot you could pick, and what's like the best? Anyone on the Zoom? Do you guys have any ideas? You can type on chat if you want to share.
I'm still a little confused on how we know if the correct number is in the left or the right side.
Okay, so I got to. Okay, somebody mentioned they're still a little bit confused about how we know whether it's on the left or the right side. If you are still confused about that part, I encourage you to look at the lecture pictures. But intuitively, think of an example. If I'm looking for the second smallest, and my left side is all, I picked my pivot that was my fifth smallest. So my left side is going to have all the numbers that are smaller than the fifth. Then my second smallest is on the left side for sure. Right? Okay. Any ideas for here? So you guys got to think. What is the best pivot? Yeah. Sorry, can you speak up? Middle of the vector. So he says the best I want is when I actually split the vector in the middle, because then when I go to the left or the right, because I could end up in either side, I'll always, or most of the time, I'll split the vector in about half. So I'll get rid of half of my problem. So intuitively, it's like, well, if I could pick the middle number as my pivot, the median, then my problem gets small really quick because I'm always splitting by half. Okay. What's the worst pivot? Somebody, yeah, back there. Yeah. The worst pivot is either the min or the max. Why? Because then it gives me one side that is essentially the entire vector except one. So if I happen to go to that side, which I probably will, right? Because it has most of the elements, then my problem only got smaller by one. Okay. So again, like you guys said, the ideal pivot is that you split it exactly in half. And now I encourage you, like, what is the running time in the case where I happen to split it exactly in half? This is the master theorem, which is saying if I have a recurrence relation, here's how you can get the big O running time. So I'll give you guys a minute to look at that and think about it. So if I happen to pick the median value as the pivot, so I always split the array exactly in half, what is the running time of my algorithm? Yeah. All right, so let's come back. Yeah, back there, what's the running time? Not quite. O(n squared would be bad if it was O(n squared. So let's pretend that's the case. This is what our recurrence relation looks like in that case. Yeah, okay, answer. Oh, okay, yeah. O(n). Okay. It will be linear. It is linear. Now you have discovered a linear algorithm. If I could pick the median as my pivot, my recursive algorithm is linear. Why? Yeah. Yeah. So this is what the recurrence relation would look like if I'm always splitting the array in half, right? I split in half and I call myself once on either the left or the right. And I do O(n) work to get the pivot. We are assuming that it takes at least linear work, right? So in that case, my A is 1, my B is 2, and my D is 1, and to the first, right? So by the master theorem, my running time is linear, right? Because I'm in the case where A, which is 1, is smaller than 2 to the first, right? So that's just, if you can write the recurrence relation, you can get the numbers. And if you can get the numbers, you just look at the master theorem. It tells you the running time. Okay. Intuitively, because I'm splitting the array in half each time, and I do linear work, most of the work happens at the top. Okay. But again, you don't need to know the intuition. Just master theorem is there. If you can, this recurrence relation you can write. So let's cover the worst pivot. So the worst pivot, like we said, is the minimum or maximum. It's also if a bad guy knows how you're picking the pivot, they can give you an array such that no matter what pivot you pick, like it'll be the minimum. So let's say like he knows you're going to pick the 4th index as your pivot. He'll put a 1 there. I mean, like this is the smallest value, right? And then your next pivot that you're going to pick is going to be this element. He'll put like a 2 there and be like, okay, this is the second smallest. So every time you're either the minimum or the maximum. So this is like a really bad pivot because this only gets rid of the 1 if that's not the one you're looking for. The left side is empty and the right side is everything else. So your array gets small, but not very quickly. Okay. And that difference actually matters a lot. Okay. So here, we haven't covered this part, but here, this is the running time of the solution you guys wrote with merge sort. So it's actually pretty good. Okay. N log n is a very, very good running time. Okay. This is like, I have an array that's of size, 4,000, and it's taking 20 milliseconds to do this algorithm. All right. This is if I always pick the worst pivot. So basically, I wrote an algorithm where I return the minimum of the array. So I always pick the worst one. And in that case, this is essentially quadratic. So if you're picking the worst pivot, it's a very bad. However, interestingly enough, if you just pick a random pivot, then the algorithm is actually really good. So that is one solution to this, which is now you know a linear time solution for the k-select problem, right? And the reason I say you know it is because we have the pseudocode, and one solution is for this get pivot, pick a random number from the array. Just pick a random one. And in the real world, that is actually how this algorithm tends to be implemented. You just pick a random one. It works out. Next week, we're going to prove that in expectation, it's linear, as in like most of the time it's linear. It is possible for it to be really bad because you're picking randomly. So you could get unlucky and always pick the smallest number, right, as the pivot. So it could be very bad, but most of the time it's pretty good. So one takeaway from lecture is you guys do have already an algorithm that is linear time for the k-select problem that essentially picks the pivot randomly. Now, what we're going to cover in the next 10 minutes is we're going to cover how to pick a good pivot not randomly. So this is like a clever algorithm that picks a good pivot, but not randomly. So if we pick it randomly, that works pretty well as long as there's no bad guy. Because if he doesn't know how we're going to pick it, then he can't give us an input that is like bad, right? But if there is a bad guy that can see what picks our algorithm is going to make, so even if we do it randomly, he like knows ahead of time that we're going to pick these particular indices, that he can give us an array where those indices are like the minimum, the second minimum, et cetera, right? So in practice, it's usually not a bad guy. So in practice, most of the implementations use the random version. But on this lecture, we're going to cover a clever algorithm to figure out a way to do this without a random version that is still linear time. Okay, so yeah, we're going to assume there's a bad guy, and we're going to come up with a really clever algorithm. And this is how now we're covering how do we pick a good pivot. So the first part of this lecture, you have an algorithm that works. Your question is, how do I pick the pivot? One answer is pick it randomly, and your algorithm will be linear in expected time. And it's actually pretty good. If you graph it, it's actually better than the merge sort. Now, like we did, first, we're going to figure out our ideal pivot. So you guys actually already talked through that. You said, I want the median. So the median would be my ideal pivot. That's not going to work. Then we're going to try to say, well, what if I get a pretty good pivot? that is like not the median, but like maybe close to the median. Okay, that is going to work. Or well, if you do a little bit of tweaks, it'll work. And then finally, that's how we're going to finish up our algorithm. So again, how do we pick our ideal pivot? So what you guys said is ideally you want a pivot that divides the input into halves. Okay. AKA pick the median. AKA pick select if A and divided by 2. Right. But that's a problem. Why is that a problem? Why would me saying like, let the pivot be, I call myself recursively on this input be a problem? Yeah. So there is one problem that I'm glossing over, which is like, you might not always be able to divide n by 2 exactly. It turns out that doesn't matter. If it's odd, it'll pick like the one slightly before the median, so it's okay. Let's assume the vector is even, but what's a problem with this recursive call? Yeah, or yeah, up here. You're very close. Actually, this algorithm would be infinite because A never gets smaller. So you end up in this like infinite loop where you just keep calling yourself because n gets smaller, right? But our base case has nothing to do with k. It has to do with how big A is. So A is always the same size. So it always is like, oh, let me get my next pivot, call it with A. Oh, for this array of size 100, I still need to get a pivot. Let me call myself. Oh, wait, for this array of size 100, I still need a pivot. Let me call myself, right? So the problem with this approach is that you can't call yourself if you're not making the input smaller. Okay, recursion only works when you're making the inputs smaller. All right, if you keep the input the same size, you get an infinite loop. If for some reason you're making it bigger, then like you also get an infinite loop, but that's kind of weird. Okay. So what if we could pick something else? So ideally, we would like to approximate the ideal world. So now we're going to say we don't want to divide the input exactly in half, but maybe about in half. Okay. Maybe this is easier. Maybe it's easier than finding exactly the median. Maybe finding some number that splits it into like a third and 2/3 is like a little easier. Maybe, right? This is actually the approach we're going to take. So again, one thing that we want to do in this class is like, one thing you would generally know is like, let's say you come up with this idea on your own. Before you go and try to figure out how do I find a number that is not the median, maybe faster, right? Would it even help is like a question you want to ask yourself, right? Like, would it even matter if I found something that's not quite half? Okay. So like I said, let's say that we're able to split the input into something between 3/10 and 7/10. Okay. For example, by the master theorem, what is my running time? Yeah. Okay, so I get one that's a running time of O of n. Okay. This is again, like I haven't told you how to do this. I'm just saying like, if we could do this, so like, do we have to split it in half? You guys, by the master theorem we walked before, if we do split it in half, we get O of n. Now I'm saying like, well, what if we don't split it exactly in half? What if we split it where the only thing we know is that we will call ourselves once on an array that's at most 7/10, right? So we only ever get rid of 3/10 of our array. So we only ever get rid of 30%. If I could do that, is that good enough? So again, here's the master theorem for a refresher. You can actually just plug in the numbers. Yeah. It's still O of n. Yes. So you actually get A1, B 10�7, D1. So you're actually still in this case where A1 is smaller than 10�7, right? So it is still O of n. So yes, if like I don't have to have the median actually. If you guys notice, it actually just tells me that I need to have something that always gets rid of a constant fraction of my array. So actually by the master theorem, you could get rid of only one 1,000th of the array, and it would still be linear. It just has to be a constant fraction. So it can't be like, oh, I got rid of one number or two numbers. It has to be a fraction of the input, right? So that's still good. So that's our goal, is we want to pick a pivot, for example, 6, that will split the two sides such that they are bounded by some fraction of the total size. We have around 4 minutes. So I think this is a lot of content for you guys to cover today. If you guys want me to keep going, we have 4 minutes. We can cover a little bit more. Yes, maybe, no, not, okay. Okay, I think we're gonna slow it down for a bit. The lecture slides are up. I will cover them on Monday. But so far, as a review, okay, the main things that we learned is, actually, let me exit out of the slideshow. So here are the key takeaways of today's lecture. There is an algorithm that uses divide and conquer to solve the k-select problem. And here's the pseudocode. If we can pick the pivot in linear time, our algorithm is linear time. We actually already know that. Okay, like that's what we covered today's lecture. What's one way to pick the pivot that is really good in practice? Randomly. Just pick it at random. And that's actually super easy to implement. And I will give you guys a hint, actually. Well, not a hint, but I did want to show you this. If you implement our super clever way that we're going to come up with on Monday to pick the pivot, the random one still beats it by a lot. So the super clever one is this green one, which is actually slower than the merge sort one. Okay. So the big O running time is going to be big O of n. So it is going to be linear running time, but it's such a complicated algorithm that the constant in front of the n is like 20. Okay. If you compare 20 to n times log n, you need 2 to the 20th for log n to be bigger than 20, right? So it actually takes some really big arrays for n log n to be slower than the one we're going to come up with. If you implement it poorly, there are better ways to implement it where it does beat merge sort, but the one where you pick the pivot randomly is always, well, you can't say always because it's random, but in practice, it is almost always faster than even our clever algorithm. All right. So that is what we will get to on Monday. I encourage you guys. So yeah, so that was, so the main thing are those two things. Any questions? Yeah. So the clever solution you'll teach us on Monday is going to be the worst time for us to be the clever solution we're going to learn on Monday is going to be a better big O complexity. So it's going to be linear. But in practice, if you implement it not very well, the constant factor in front of the n is actually pretty big. So it's worse than n log n in practice for like, unless your array gets to like 1 million, it's worse, right? So again, the big O only tells you in like really large cases. So this is an example where in the real world, you might not implement this clever solution because of all the cleverness, it's actually slower. Even though the big O is linear and the second one is like n log n. So you're like, oh, that must be worse. Not always the case. Okay. Yeah. Any other questions? How was lecture today? Did you guys get some, learn some stuff? If you guys want to look ahead, you can look at the slides. It is also called median of medians is what we're going to cover for like how to pick the median. Yeah. Cool. Chat, let's see. Somebody mentioned there's a codependency. Yes, there is going to be a codependency, Trinity. You're right. All right, everybody on Zoom, thanks for coming. I will see you guys on Monday.